For this example, we want to sketch the graph of the function f of x is x over x squared minus 4, and do so using all of our calculus techniques we've developed so far. Look at the function itself. What can I see right off the bat? Well, I know this will have a 0 at x equals 0 because that's where the top is 0, so the whole thing is 0. I also see that I will have vertical asymptotes at x equals plus or minus 2 because that's where the bottom factors and where the bottom is 0. And also I have a horizontal asymptote at each side at y equals 0 because the degree of the denominator is more than the degree of the numerator. I can also analyze the asymptotes briefly. So this function here is going to be x over x plus 2, x minus 2. So if I look near the asymptote at x equals minus 2, if I'm to the left of that, I'll be at, say, like negative 3, in which case the top is negative, and the bottom is minus 3 plus 2 is a minus 1, times minus 3 minus 2 is a minus 5. The whole thing is negative, which means it's going to be going down near that asymptote to the left. And on the right, I will now have a negative on top, a negative with the x minus 2 term, and the x plus 2 will be positive, so this is coming from the top here. And then near x equals plus 2, I will see the same pattern again. Then if we're coming from the left, that's at plus 1. The top is 1, which is positive. The bottom is 3 times negative 1 is negative. Going to go down here and come in from the top because if I plug in 3, I get an all positive number, so every term there is positive. Okay, now to find increasing, decreasing one, look at the derivative. What's the derivative here? Well, if f is x over x squared minus 4, then the derivative here is going to be x squared minus 4 times 1 minus x times 2x all over the bottom squared. Now the quotient rule, which just becomes x squared minus 4 minus 2x squared, x squared minus 4 all squared, or negative x squared plus 4 over x squared minus 4 squared. If you look at this function, what you notice right off the bat is this function is never positive because this x squared plus 4 is always positive. This is a something squared, so it's always positive, and it has a minus sign. So this is actually always negative, which means the function is increasing never and decreasing always, but I have to also account for the asymptote. This function will be increasing never and decreasing everywhere, but I have to account for the asymptote. So it'll be decreasing on negative infinity up to minus 2, the first asymptote, minus 2 up to 2, the second asymptote, and then 2 up to infinity. This also means we have no critical points and no local maxes or mins. Now for concavity, I want the second derivative. And since my first derivative was negative x squared minus 4 over x squared minus 4 squared, putting the minus sign on the top, I can find the second derivative by the quotient rule like always. And this I can cancel an x squared minus 4 from every term. So this here drops to a 3. This drops to a 1, and this one goes away entirely. I can then distribute the top. After realizing that I can cross out this minus sign and these two minus signs here, make my life a little bit easier. That's a 4x coming from in here. So that is a 4x cubed plus 16x all over x squared minus 4 cubed. So we'll find the top, 2x cubed plus a 24x. X squared minus, which can be factored on top as a 2x times x squared plus 12 all over x squared minus 4. So for this, I have 3 cut points to worry about. The 0, that's here when x equals 0, as well as the 2 asymptotes. Let's draw that number line. I have the 0 that's in there. I have the 2 asymptotes at minus 2 and plus 2. And one thing to note here, this term here is also always positive. So that's always going to be positive no matter what I do. If I plug in minus 3, I get a negative sign on top. On the bottom, I will have x squared minus 4, which will be 9 minus 4, which is a positive number, cubed. It'll be minus over plus, that's a negative sign, so that's where it's going to be concave down. If I plug in minus 1, I'll get negative on top, and on the bottom, I'll get a negative sign cubed, which is still negative, so I'll get a plus sign here. Crossing over 0, then at 1, I will see plus on top and minus on the bottom, so that's minus, and then over here, I'll get pluses everywhere. This means this function is concave up on minus 2 to 0 and 2 to infinity, and it's concave down on minus infinity up to minus 2 and then 0 to 2, which means there's an inflection point at x equals 0. as it's before we know this point's at. Now let's go ahead and draw the graph. So for this graph, I know I have two vertical asymptotes, one at -2, one at +2. And with the point at 0, 0, I have horizontal asymptotes at 0 on both sides. And to know my behavior near both asymptotes, it's down here and come in from the top, and then down here and come in from the top. And I know that 0 is going to be an inflection point. So now you just piece out the graph from there. The asymptote, I go down, and note I'm always decreasing. Decreasing through the asymptote, and make it from the top. Now I'm concave up during this area, hit the point here, become concave down, and then go to the asymptote, and then drop from this asymptote and go to the horizontal asymptote, just like that. And there's a sketch of what this graph might look like. The shape's not going to be exactly right, but the general behavior, what's going on in the shape of the curve, is correct for this graph. Let's we use all of our calculus information to sketch out the graph of a function from it and the signs of its derivatives of first and second order.